Welcome to the lesson on trigonometric ratios. At the end of this lesson, you will be able to state the trigonometric ratios of an acute angle in a right-angled triangle. You will also be able to calculate the trigonometric ratios of an acute angle using Pythagoras theorem. Here's Jack. He has been given a unique problem in his math activity class. He has to find the height of the clock tower in the campus of his school. Tough job. Actually, there is a branch of mathematics called trigonometry, which can be applied to solve Jack's problem. The word trigonometry is derived from ancient Greek words, which mean study of triangles. Trigonometry is the study of how the sides and angles of a triangle are related to each other. In this lesson, we will study the ratios of the sides of a right triangle with respect to its acute angles. Let's begin by reviewing some key terms related to right-angled triangles. You may already know some of these. Triangle ABC is a right-angled triangle. A right-angled triangle is also called a right triangle. In this triangle, angle ABC is a right angle, as it measures 90 degrees. Angle BAC and angle ACB are acute angles, as they measure less than 90 degrees. Please note that angles can also be named by the vertex when they are formed. For example, angle BAC can be referred to as angle A, angle CBA as angle B, and angle ACB as angle C. The longest side of the triangle is side AC, which is opposite to the right angle. This side is called the hypotenuse. Now, consider angle A. Side BC lies opposite to angle A. Let's call it the side opposite to angle A. Side AB lies next to angle A. It is said to be a side adjacent to angle A. Similarly, let's consider angle C. Side AB is the side opposite to angle C, while side BC is a side adjacent to angle C. Note that the terms opposite and adjacent change based on the angle being considered. The hypotenuse, however, remains the same. Now, let's come back to Jack. We'll move Jack to a position such that a line can be drawn joining the top of the clock tower and Jack's head. Oh, looks like the top of the tree also falls on the same line. Let's drop perpendiculars from this line to the ground, passing through the clock tower, the tree, and Jack. We now have three right triangles: triangle PQC, triangle ABC, and triangle MNC. Angle C is common to all the three triangles. Each triangle has one angle, which is a right angle. It means that two pairs of corresponding angles of the three triangles are equal. Thus, by the angle sum property, the third pair of angles of these three triangles is also equal. This means that the triangles PQC, ABC, and MNC are similar to each other by the AA similarity criterion. Now, what can we say about the corresponding sides of these triangles? Recall that in case of similar triangles, the three pairs of corresponding sides are proportional. This means that the ratios PQ upon PC, AB upon AC, and MN upon MC are equal. Now, let's consider angle C in all the three triangles. In relation with angle C, sides PC, AC, and MC are all hypotenuses, and sides PQ, AB, and MN are all sides opposite to angle C. Thus, we can see that, with respect to angle C, the ratio of the opposite side and the hypotenuse for all the three triangles are constant. This constant ratio can be written as opposite side of angle C divided by hypotenuse. In trigonometry, this ratio is given a name. It is called the sine of angle C. The sine of angle C is written as sine C. Here, angle C is an acute angle. The sine of an acute angle in a right-angled triangle is defined as the ratio of the side opposite to the acute angle and the hypotenuse. Similarly, in relation with angle C, sides PC, AC, and MC are hypotenuses, and sides QC, BC, and NC are sides adjacent to angle C. The ratio of the adjacent sides and the hypotenuse is also constant. This constant ratio is named as the cosine of angle C. The cosine of angle C is written as cos C. The cosine or cos of an acute angle in a right-angled triangle is defined as the ratio of the side adjacent to the acute angle and the hypotenuse. Similarly, for triangles PQC, ABC, and MNC, the ratio of sides opposite to angle C and sides adjacent to angle C is constant. This constant ratio is named as the tangent of angle C. The tangent of angle C is written as tan C. The tangent or tan of an acute angle in a right-angled triangle is defined as the ratio between the side opposite to the acute angle and the side adjacent to the same acute angle. Let's recap the three trigonometric ratios that we just discussed. The table shows the trigonometric ratios for an acute angle of a right triangle. The measure of the acute angle is taken as theta. Now, here's an easy way to remember these trigonometric ratios. Look at the bold letters. They form a mnemonic. So, ka, to. It is pronounced so, ka, to, a. The so stands for sine of an angle is opposite side over hypotenuse. The CA stands for cosine of an angle is adjacent side over hypotenuse. The TOA stands for tangent of an angle is opposite side over adjacent side. Memorize this to remember these ratios. Apart from the three primary trigonometric ratios, the reciprocals of these ratios are also defined. The cosecant or cosec of an acute angle in a right-angled triangle is the reciprocal of the sine of the angle. Thus, the cosecant of angle C or cosec C is equal to the ratio between the hypotenuse and the side opposite to angle C, or the cosecant of angle C is equal to AC upon AB. The secant or sec of an acute angle in a right-angled triangle is reciprocal of the cosine of the angle. Thus, the secant of angle C is equal to the ratio between the hypotenuse and the side adjacent to angle C, or the secant of angle C is equal to AC upon BC. The cotangent or cot of an acute angle in a right-angled triangle is reciprocal of the tangent of the angle. Thus, the cotangent of angle C is equal to the ratio between the side adjacent to angle C and the side opposite to angle C, or the cotangent of C is equal to BC upon AB. Here are all the 6 trigonometric ratios of an acute angle of a right triangle. The values of trigonometric ratios do not vary with the lengths of the sides if the angles remain the same. Thus, we can conclude that trigonometric ratios are only dependent on the ratio of the sides and not on the lengths of the sides. An important point to note is that when the square of these ratios is written as sine square c in place of sine c square, this applies for all trigonometric ratios. Let's try an example. Consider a right triangle ABC. Its two sides are 3 units and 4 units respectively, and its hypotenuse is 5 units. For angle C, the opposite side is AB, which is 3 units, and the adjacent side is BC, which is 4 units. Let's find the trigonometric ratios for angle C. Sine C will be equal to opposite side to angle C divided by hypotenuse, which is equal to 3 divided by 5. Cos C will be equal to adjacent side to angle C divided by hypotenuse, which is equal to 4 divided by 5. Tan C is equal to opposite side to angle C divided by adjacent side to angle C, which is equal to 3 divided by 4. Cosec C is reciprocal of sine C, hence it is equal to 5 divided by 3. Sec C is reciprocal of cos C, hence it is equal to 5 divided by 4. And cot C is reciprocal of tan C, hence it is equal to 4 divided by 3. Now, consider the other acute angle, angle A in the right-angled triangle ABC. Are the trigonometric ratios for angle A same as those of angle C? As you can see in the table, the trigonometric ratios of angles C and A are different since their adjacent and opposite sides are different. In case of the trigonometric ratios of an acute angle in a right-angled triangle, if any one of the ratios is known, all the other trigonometric ratios of the angle can be calculated. We'll apply this understanding to help Jack find the height of the clock tower. In triangle MNC, side MN, which represents Jack's height, is equal to 6 feet, and side NC is 8 feet. With reference to angle C, MN is the opposite side and NC is the adjacent side. Thus, tan C is equal to opposite side to angle C divided by adjacent side to angle C, which is equal to 6 divided by 8. On simplifying, we get 3 divided by 4. Now, the distance between point C and the base of the clock tower, which is represented by side QC, is 40 feet. In triangle PQC, side QC is the side adjacent to angle C. Let's assume the height of the tower, which is represented by side PQ, as x. Tan C is equal to PQ divided by QC, which is equal to x divided by 40. We know that tan C is constant. Thus, ratio of PQ and QC is equal to ratio of MN and NC. Substituting the values, we get x upon 40 is equal to 3 upon 4. On simplifying, we get the value of x as 30 feet. Therefore, the height of the clock tower is 30 feet. Let's solve some more examples. Here, one trigonometric ratio is given. We will use this ratio to find the other trigonometric ratios. Consider angle C in the given figure. It is given that cos C is equal to 4 by 5. Now, cos C is equal to the ratio between its adjacent side BC and hypotenuse AC. Thus, we can say that AC is equal to 5x and BC is equal to 4x, where x is some constant. The reason we include a constant x here is that the trigonometric ratio just gives us the proportions of two sides, not their exact values. In both these triangles, cos C is 4 by 5, though the actual lengths of their sides are different. Now, using Pythagoras' theorem, we can find the length AB. Putting in the values and simplifying, we find AB is equal to 3x. Since we know the values of all the three sides of triangle ABC, we can calculate all other trigonometric ratios. For example, sin C is equal to 3x upon 5x, or 3 by 5. Similarly, tan C is equal to 3x upon 4x, or 3 by 4. Let us take another example. Suppose in the given right-angled triangle ABC, sin A is equal to 2 by 3. Now, sin A is equal to the ratio between its opposite side BC and hypotenuse AC. Thus, we can say that AC is equal to 3x and BC is equal to 2x, where x is some constant. Again, using Pythagoras theorem, we can find the length AB. Putting in the values and solving, we find AB is equal to root 5x. Now, since we know the values of all three sides of triangle ABC, we can calculate all other trigonometric ratios. For example, cosine of angle A is equal to root 5x upon 3x, or root 5 by 3. Similarly, tangent of angle A is equal to 2x upon root 5x, or 2 by root 5. This brings us to the end of our discussion on trigonometric ratios. Memorize these ratios by heart and try finding these ratios in different right-angled